Hello, hackers. So hopefully, by now you guys have gone through the slides explaining how the heap and the Tcache in general work. So now we'll be walking you guys through how to actually exploit the Tcache using the Python library Poon tools that we've been using all along, right? So usually when we do heap exploitation, the important question we have to ask is can we read or write to free chunks or memory? And what can we actually achieve by doing so, right? So imagine a scenario where you have some pointer that you've been freed, right? But for some reason, the program doesn't clear the pointer. And instead, it actually allows the user to write into the pointer. So what happens then, right? Now, if we go back to how the Tcache looks like as a linked list, you'll remember that um, the way the chunks are linked is that in the first 8 bytes of each chunk, there's going to be a little endian number that represents the address of the next chunk in the list, right? So over here, you can see that at the head, this first chunk over here has a pointer or an address that points to this next chunk over here. And because the list ends at this last chunk, the the pointer here is set to the 0 or null, right? So now the important question is, since the chunks are linked together through these pointers in each chunk, what happens if we are able to actually write into the chunk over here? So imagine if let's say we could like actually do that, and you'll notice that because we could write into that chunk over here, you'll see that the pointer that links the chunks together, like these 8 bytes, uh, because we've overwritten them with our own data, now the pointer has been replaced by some invalid address or garbage data that we just wrote into it. And so, because of this, the list itself has been corrupted because you'll see that the Tcache thinks that the list starts from this chunk and that the next chunk of the Tcache will be living at this address over here, which is not true, right? So, just to show this an example, if we walk through the infant heap challenge yet again, and over here I'm just gonna run ponynet. Right, so as we wait for ponynet to finish making the binary, one thing to ask is, since we've corrupted the Tcache and we've caused the chunk pointers to point to somewhere invalid, what happens when we actually try to allocate from the Tcache bin, right? So if you remember, right, uh, when we allocate first, the Tcache will return what is at the head of the bin, and then it will pull up the next chunk and link it into the head over here, right? So now we've done one malloc, and the malloc has returned this chunk. Uh, so ideally, because our count is still non-zero, when we malloc again, the Tcache will try to return this address, and probably the program is going to crash, right? To see that in action yeah, it's finished linking. So I'm going to go ahead and open the patch binary in GDB over here. And what I'm going to do is I'm going to run it. And first things first, we want to replicate the exact scenario here where we have two chunks in the Tcache. So that means what we need to do is we need to allocate two chunks, 1 and 2, and then we have to free them, free both chunks so that both go into the Tcache with a count of 2 over here. So let's do that over here. I'm gonna enter the option 1. Let's put our chunk address in the first entry of the array, so index 0, right? And I'm gonna choose 256. So because it's a nice number, 256 is 100 in hexadecimal. So we've gone ahead and allocated our first chunk. Let's go ahead and allocate our second like so. All right, so notice because the sizes of both chunks are the same, right? When we free them both, they're gonna go into the same T cache, right? So just to show you over here, these two chunks have the same size. You'll see that this chunk, the first one that we allocated, has a size of hex 110, with the extra hex 10 bytes being because of the metadata I hid over here, right? And similarly, so for the second chunk. So now what I'm gonna do, I'm just gonna go ahead and free the chunks, right? But instead of freeing them in the same order that we allocated them, right? For example, we allocated this chunk first, and then we allocated this chunk next. Um, Instead, we're gonna free this chunk first. We're gonna free this yellow chunk first, and then this red chunk next. And if you recall, why we're doing this is because uh, you remember that the Tcache essentially is a last in, first out, right? And what this means is that whatever chunk that we've put in the most recently into the Tcache, right? When we allocate it back, we're gonna we're gonna get it back the first time. And this is because all the chunks in the Tcache are linked into the bin at the head, right? So if you go back over here, the first time we put a chunk into the Tcache, it's gonna be linked at the head over here, right? So this is gonna be the first chunk that we put into the Tcache. And then when we free the next chunk, right, instead of adding the chunk to the head, I mean to the last chunk over here, what we're gonna do is the Tcache is gonna link it at the head of the bin, right? And after that, it's gonna set the pointer for that that last chunk that we freed to point to the first chunk, right? So let's just do that real quick. I'm gonna free the second chunk, right? So index 0, index 1 over here, and then I'm gonna free the first chunk that we allocated next. And if you see now, I'm gonna show you guys the visual heap view, right? So you do this with the this command. Um, you'll see that the chunk that we just freed, which was our first chunk here, right? It now has a pointer, which is basically the address of the next chunk that's in the bin, right? Uh, Notably so, there is also this second pointer, but for now we don't have to care about that. It's just another piece of metadata when you put a chunk into the Tcache, right? But yeah, let's look. You'll notice that the last chunk that we freed, index 0, has this pointer in the first 8 bytes that points to the next chunk in the Tcache. And if we look at the bins, you can do this in GDB or Jeff with the heap bins command. We do this, you'll notice that the head indeed is our first chunk, 4052A0, this chunk. The first chunk that we allocated and then the last chunk we freed, right? So this is the head, and then this is the next chunk, which was this second chunk over here. Okay, so now what I'm gonna do, I'm gonna edit. I'm gonna edit our last chunk that we freed, this index 0 chunk, right? And let's see what happens. So I'm just gonna type a bunch of random characters into that first chunk. And if we take a look at the heap again, this was the chunk that was at the head of the Tcache, right? And you'll notice that now the 8 bytes uh, do not resemble a proper pointer or a proper address, right? Before, the first 8 bytes was the address of this second chunk over here. But now, because we overwrote it, it's some random number converted from what we just typed, right? If we take a look at our bins, you'll notice that Jeff actually fails to parse the next chunk in the bin because we just overwrote the pointer. And indeed so, if we try to allocate from that same Tcache again, right? I'm gonna allocate 2 times, so we get back the second chunk in the Tcache, right? I try to do this. You'll notice that we crash, and this is because malloc is trying to write to a certain, or it's trying to read from a certain address, right? The address in this R8 register. We try to print what's in R8. You'll see that it's exactly the nonsense that we just typed into the chunk, right? So you'll see that, yeah, because we managed to override the pointer with some random characters, uh, the program crashes. But now an important question to ask, right? And you always ask this no matter whether you're doing heap exploitation or stack exploitation, right? The essential question is if we can make the program crash, right? Can we somehow get it to not crash, but still do what we want to, right? Like for example, in the stack exploitation, remember that you could cause the program to crash because you overrode the return address and the program attempted to return to some invalid function address, right? But you also knew that because you can override the return address, you can override the return address with an actual valid address that points to some other function, right? So the same thing here in the heap. Because we can override the Tcache pointer, right? Or at least the next pointer, what we call the next pointer in the chunk, right? Or the pointer that points to the next chunk in the Tcache, right? Because we can override it with nonsense and garbage data, can we override it with an actual pointer in memory? So that's a very good question because this technique is basically what we call Tcache, and it's basically uh, when we are able to corrupt the free list or the Tcache bin free list, right? By changing or writing into the next pointer of the free chunk so that it points to some other address, and we're able to get that address back from malloc, and we're able to use that address to read or write certain data, right? So going back to the scenario where we have 2 chunks in the Tcache, now we have our write into this free chunk over here, and there is a pointer that points to this next chunk. And let's say somewhere in memory, maybe it's in the elf binary, right? There's a certain address that contains a kind of secret string that we want to read. We want to be able to read, right? So instead of overwriting the next pointer with whatever data, let's overwrite it with the actual address of this secret string. And because the Tcache completely trusts this pointer over here, when we try to allocate from the Tcache again, so we malloc once, this brings our next chunk, the second chunk, to the head of the bin. And if we malloc again, you'll notice that it returns the actual secret address that we want to read. And so we can just simply read from that address. And just as easily as we could read from that address, it also means that we could write to the address. Right? So let's just to put it into perspective, why do we need to go through all this trouble to get an address that's outside of the heap, right? Well, remember that because the program uh, assumes that all the chunks or everything that you're gonna get back from malloc is gonna come from the heap. It assumes this, right? And so it lets you uh, read and write into the chunk that it gets back from malloc, right? But that assumption now is wrong because since we can get the Tcache to return an arbitrary pointer, right? Or basically whatever pointer we want or whatever address we want. That means we can also read or write to whatever address we get back from malloc. And so that's why we need this Tcache processing technique. Okay, so what does this show? Because we can control what address the Tcache returns to us, uh, this is only possible because we can actually write to the chunk after it has been freed, right? You'll notice over here, after it frees the address in this array entry, the chunk array entry, right? It doesn't do something like chunks. It doesn't clear the pointer, right? And so, because it doesn't clear the pointer, it doesn't do something like this. It just frees the address. That address is still inside this array. And what that means is that the program still allows you to choose that address uh, to read or write into that address, right? And this vulnerability is what we call a use after free. It's called a use after free because we can use the chunk after it has been freed, right? In short, this is called a UAF, or the initials of the use after free. And sometimes there might be some limitations. In this version, it's old enough that it doesn't care about whether the address is aligned. But in the newer versions, where there are more mitigations enabled in the Tcache, uh, some restrictions might be that the the pointer that you modify this next pointer to, right? This one over here, usually has to start with a zero in the first digit, right? And this is kind of because of chunk alignment, because the heap assumes that all chunks are aligned to some multiple of 16 bytes, right? Or in a hexadecimal, it's hex 10. So usually it will enforce this mitigation, but probably because this libc is kind of old, it doesn't really care. So yeah. Whew. Okay, so that was a lot to take in. But now the question is, uh, you have this ability to read or write to whatever address you can think of, right? But if let's say you want to do a very specific thing or a very specific malicious action that allows you to run code, where exactly should you write or allocate to? Where exactly or what exact address should you change this pointer to so that it gives you back that address and you can do stuff that allows you to get code execution, right? Or in this case, pop a shell. So this is what we call write what where um, to exact meaning execution, right? Basically, where can we write data that allows us to pop a shell? So let's go back to the ELF binary, right? In the ELF binary, and this will come in important later, there's a certain thing called the PLT and the GOT. What it stands for is basically the procedural linkage table and the global offset table. And this might sound like a kind of an abstract name, but basically what it is like if I disassemble the code in one of the functions here in the binary, let's say main, you remember that all of the functions here, they use some sort of libc function that's usually not stored in the binary. Right over here, it calls this it doesn't actually call the libc function, as you can see. It calls a kind of like a weird function inside the binary that's called a PLT stub, right? Procedural linkage table stub. And if we disassemble what this actually does, you'll notice that it does a jump, and it does a jump into some address that's stored in the binary itself. You can see over here, GDB has nicely labeled this as the GOT for printf, right? And the GOT is basically what we call the global offset table. And to explain this, I'm just going to run it over here. And if I do the GOT command, what it shows is that in the binary, there's like a table of addresses for each function, right? And for each entry in this table, there's going to be the actual libc address uh, of the function that the binary wants to call. In this case, let's say setbuff, right? If we examine this address over here that's stored in this entry, you'll see that indeed it corresponds to the actual libc function for setbuff, right? And uh, you'll notice also that in the other entries, instead of the libc addresses themselves, these are actually inside the binary. And this is because uh, before before each function is called, right? Uh, the this function what this function does is that it looks for the actual libc function or the address of that function inside the libc. So it searches in the libc, and once it's found the address of the actual function, it will store it inside the table so that whenever the binary needs to call this libc function, it doesn't need to look for the address inside the libc anymore. It doesn't need to search, and it can just like jump into whatever is inside the corresponding entry, right? Kind of like what you might call a cache, right? In the sense that it saves data that you already searched for so that execution is faster. Yeah, but uh, this is important for us because uh, if we know that whenever a binary is calling intends to call a libc function, it actually calls whatever is inside this table. If we can somehow overwrite this entry to point to, let's say, system, right, or whatever function we want to, and the binary calls this this GOT entry function, then essentially instead of calling the real function, it calls what we wrote there, right, the libc address. And to kind of show that, I'm gonna run first, and you'll see the GOT has been loaded. Some functions have their libc addresses, and the I'm gonna find what the system address is first. Okay, so this is the address of system, and now something I'm gonna do is I'm basically gonna write to this entry. Let's choose free. Right. I'm gonna set this to this address over here. Okay, so just to check, let's run the GOT command again, and you'll see that we've overwritten this GOT entry to system, right? Now, if I continue, I set say I allocate some chunk. I'm gonna put uh, the binsh string over here, and let's try to free this chunk now, right? You'll see that instead of actually freeing the chunk, it calls system on our chunk, which contains the binsh pointer or the binsh string, right? And because free now calls the system instead, what essentially it does is that it does a system binsh instead of a free, and that gives us our shell. So our goal in this challenge is basically to achieve exactly that, to be able to write to this GOT entry, the free GOT entry, so that when free is called on whatever chunk we want, and our chunk that happens to have this binsh string, it will give us the shell instead. Okay, so so uh, basically what makes this possible, why we can write to the GOT table, is because there's a protection that isn't enabled, what we call a railroad or read-only relocation, right? And what this does usually is that if it's a full railroad, If the protection is enabled and is full error, normally we shouldn't be able to write to the GOT table, right? So because it's partial error, we can do this. And of course, the vulnerability is what we talked about, the use after free. So what we're gonna do, like what we just demonstrated in the GDB over here, is we're gonna overwrite the GOT entry for free to point to system, so that when we free our chunk and the chunk has the benefit string, it's gonna pop a shell for us, right? So that's the plan of attack right now. First, we're gonna have to leak libc, and then using our Tcache poisoning, right? We're gonna be able to change the Tcache pointer to the GOT address, right? And once we get the GOT address from malloc, right, because we've done Tcache poisoning, we can overwrite the entry with system. And once we free a chunk with the benefit string, we should get our shell. So let's go ahead and implement this, right? Just to check, this is indeed the right binary. We have the partial railroad uh, mitigation on, no PIE. So that means the addresses for the GOT table entry is going to be static. And Ponynet has given us a template. So let's just go ahead and use this. Okay. Now, the first thing usually what we need to do when we're writing a heap exploitation script, usually it's quite helpful to write what we call helper functions, right? And these are basically functions that allow us to do malloc. Let's say index size, edit, let's say whatever, uh, so and so, because uh, we have to remember that when we're interacting with the binary through our script, we're basically replicating what we're doing if we actually run the binary ourselves. So if you were a human running this binary, how you would interact with it is you type one over here, you press enter to send that option, right? And the index you just like press whatever index on your keyboard, you press enter and to send it, and so on and so on, right? But the thing is, if you were to replicate this in the solve script, what you would do would be something like r.send line after such and such, uh, and then you want to choose the malloc, right? So you send that option, and let's say you want to allocate um, whatever index you want. So in this case, it would be a 0, right? And let's say you want the size to be something like 256, like we usually choose. Now, each time you want to do a malloc, you have to copy this set of code, right? You have to copy this each time, and if you want to do another malloc, let's say for index 1, right? We have to change this to 1, and so on and so on. And it gets a bit tiring to do, right? In a CTF, uh, things that you want to prioritize usually are the speed that you solve the challenge, but also readable code, right? Because when you're doing a CTF, sometimes you'll be so stuck or deep inside a problem that it gets a bit hard to think about what you're actually writing. And that's when it helps to have a readable code because number one, uh, it's easy to understand when your brain is all tired and spent on actually figuring out the problem. And number two, if let's say you want to look back on a previous problem that you did, right, in let's say Pwn, then it's very easy to read through the script and then be able to understand what you're actually doing. So this is why we have helper functions, right? If instead of doing like copying these three lines again and again, what if instead we could just do something like just call this function malloc, and we choose an index of 0 and 256 as the size. And this would accomplish exactly what those 3 lines of code were doing, but using only 1 line, right? And that becomes really useful. So let's go ahead and implement these helper functions, right? To do this, I'm gonna remove this main function over here because it kind of gets in the way. Usually, it would be good practice to have a main function so you don't run everything in the global scope. But because this is just a CTF script, it doesn't really matter, right? I'm gonna change this to yeah, conworks, and then over here, we're gonna implement the logic for doing a malloc, right? So if you remember correctly, the actions that we do with a malloc is you send 1, and then you send the number that you want for the index, and then you send whatever size you want, and then that's it, right? So similarly in the script, what we're gonna do is the exact same. We're gonna wanna send the first option, number 1. It's recording. Yeah, it's recording. And then we're gonna send the index, right, as a number. But we don't know the index yet when we're writing this function. So instead of hard coding it, we're gonna convert this index to a string, right? And because Pwn tools expects bytes instead of strings, as indicated usually by this B before the quotation marks, we're gonna do a dot encode over here. And what dot encode over here, as you can see, it encodes the string uh, and converts it to bytes, right? So this is especially useful. And we're gonna do the same thing for the size over here, because both are numbers, right? Okay, so that's one helper function down. We have 4 helper functions to write over here. So let's go ahead and implement those as well. For the free function, all you need is the index. So same thing over here. We're gonna send our menu option, but instead of 1, it will be 2, because over here the free option is number 2. Okay, so send number 2, and afterwards we're gonna send our index, and like so, exactly as we did with the first function, we're gonna convert it to a string and then encode it so that it becomes a byte string. Right, next function. So we have 2 functions down, number 1 and number 2. We gotta implement the edit function now. Okay, so how does the edit function work, right? We send number 3 when we're in the menu. We choose what index we want to read. Okay, so over here it's because we haven't allocated. So I'm gonna allocate it, and now if I choose the number 3, I wanna edit the first chunk, right? Index number 0. So I'm gonna choose the 0 over here. And you'll notice that it will ask us for the content that we want to write into. And you remember what I did earlier is that I entered a bunch of characters. So this is kind of important to take note, right? When the program is asking for content, it's actually expecting raw bytes, right? And another thing to take note, okay, so because it expects raw bytes, we're not gonna be converting the content to a string. So over here, I'm just gonna make the function header. This index is gonna be a number, right? But this content over here is probably gonna be some byte string that we pass into the function, right? So we're gonna set up everything from the menu option to the index selection as we did before. But now when we want to send our content as raw bytes, what should we actually do? Right? If you remember from last lesson, how the previous trainer would do it is that he would do a send line, and afterwards he would just pass in the content, right? Because the content is a byte string, right? How we would use it is we would do like something like edit 0, and then whatever we want to write into the chunk. And usually the trainer would do it something like send line after. Uh, However, there is something that we need to note over here because there is a difference. If you go back to the source code for the program, right, you'll notice instead of doing like an fgets call, as we saw earlier in the example, yeah, over here, instead of doing an fgets call over here, it's actually doing what we call a read, right? And in C, a read kind of does the same thing as fgets. It takes in the user input as raw bytes. However, one difference is that while the fgets call, uh, it will stop reading your input when you enter a new line, right? The read function may not necessarily stop reading when you enter a new line, right? And this can be kind of confusing for beginners because uh, to you, when you run the binary and you're sending input, right, you'll notice that when you press the enter function over here, you say, hey, when I press the enter function, it does send the input and it stops reading, right? So what's the difference? Uh, the thing is that you have to remember that the keyboard is kind of different. Entering inputs into the keyboard is kind of different from uh, sending in input from a program, right? When your keyboard uh, sends this new line, what it's doing on the side is that other than a new line, it's selling what we call an end of file character, EOF. And this is a kind of special control character that indicates that the input has stopped sending. It's like the input has terminated, and it the program should stop reading. But the thing is over here, when do when we're uh, when we're sending input from our program, right, and we do send line, actually the read call, instead of stripping away the new line that you send with your enter function, your enter keyboard, right? It's gonna read it in as a character as well, and maybe it will stop reading your input because in Pawn Tools this sends a EOF character as well. But additionally, it's gonna read in your new line as well. Okay, so to demonstrate this, I'm gonna go into GDB. We'll create the chunk, and let's say over here I added the chunk. I'm gonna enter some random characters, right? You'll see that other than the characters that I entered over here, 7374, 7365, whatever, right? There's also this 0A character at the end of our input. And this 0A is precisely the new line character, right? It's there because when we send a new line, the read function also reads it in as input, right? And then after the new line, there's this EOF character, so read stops reading, but it will still read this new line character. Okay, so this is kind of important. Uh, if you remember from the last lesson, there was a challenge where you had to partially overwrite the the first few digits of the address, right, to bypass PIE or something like that, right? And uh, you realize that this was if you were doing that challenge and you had to overwrite this you had to partially overwrite an address over here, let's say. If you send in this new line, it's gonna cause some problems, right? Because it's gonna overwrite part of your address, and potentially it's gonna be an incorrect address. So what we're gonna do instead of doing a send line after here, we're gonna do a send after. And the difference in this for pawn tools is that send line after will send this new line character, right? Send after does not send the new line character, but the program or the binary is still gonna register that the input has stopped being sent, and so it's still gonna be okay. And in fact, to kind of demonstrate this, right, let's try to run our program, attach our exploit script, the Ponto script, to our binary. And what I'm gonna do over here is set, I'm gonna attach GDB, right? But before I do that, there's something that I must enable. And this is something for my own computer. You don't have to do this on your other machine. Right over here, I'm just gonna paste in this line. It's for my own setup. But when I run this script and I attach GDB, okay, that's weird. I believe it's because of the weird con function that I don't particularly like, but I'm just gonna do it manually over here. So if I run this, we've attached GDB over here, and my helper functions just ran. It did a malloc and did an edit, right? If I check the heap now for our chunk, you'll see that the content that we wrote into the chunk is there, but no new line was sent after, right? And this is good. So precisely what we told our program to send, it sent it and just that. It sent only that, right? It didn't add the new line, so this is good. So that's just some considerations when you're writing exploit script like this, right? Do you want a send after or do you want a send line after? And the general rule of thumb is that if you see a function that uses the read function instead of something like fgets or scanf. Scanf is this function that parses your input into a number, but basically it also reads up to the new line, right? If it's something like this function, then okay, use send line after. But if it's something like a read over here, then it's probably more viable to use send after instead. Okay. And afterwards, we're gonna implement the helper function to read from the chunk. So it's gonna be read index because it only asks us for the index, right? And this is option number 4, as you remember. Okay, so now you'll see that what it does is that it prints this content line, right? So this content word, and then a semicolon, I mean a colon and a space. And then afterwards, it writes the raw bytes from the chunk into what we call standard output, right? Basically the terminal screen. The question is, in our Ponto script, how do we actually receive those bytes and turn it into a number, right? Because you remember that usually when we leak stuff, it's going to be printed to us in the form of bytes. We want to be able to convert those bytes from little endian into a 64-bit number that we can work with easily, right? And the way we do this in Pontos is that we have a receive until function. What this does for Pontos is that basically it tells Pontos, uh, as you're receiving the bytes from the program, I want you to receive up until you see up until you see a certain delimiter, right? Uh, let's say over here we set this delimiter to content because uh, the program also prints this content line and we want to receive up to here. And what Pontus will do is that it will do, oh, okay, so I see this piece of string being printed out. I'm gonna stop receiving for a bit, right? And then uh, this is useful because afterwards we want to receive uh, the bytes that are being printed from the chunk right over here. So once Pontus stops reading up to this content and this content string, and we tell Pontus again, oh, so you stop there. please receive 8 bytes, right? Pontools will say, okay, so I've stopped over here. Now this uh this write function has been called. It's printing the bytes from the chunk onto the screen. I'm gonna receive from there onwards, and specifically only 8 bytes, right? And if let's say we didn't have this receive until, right? Let's say we only do a receive 8 bytes. Instead of parsing the bytes that are printed from this write function, right? Some of it is gonna be uh, it's gonna receive like these bytes over here in the content string. And this isn't particularly useful for us because that's not what we're trying to leak, right? So it will receive these bytes and then it will return it to us, but that's not what we're trying to leak. So that's why we need this receive until, right? And once you receive like the 8 bytes from those chunk, what we're gonna do is we're gonna convert it into a number, like a 64-bit number from little endian, right? As you remember from last week. So we're gonna convert it from little endian, and this is gonna be our leak, like so. And we can just return it like that. Okay, there's one thing we've missed out though. I forgot to send what index I want to write from. So I'm just gonna put that over here and we are done. Okay, so we have our helper functions implemented over here. Now the question is, if you remember, the first step in this solve is gonna be somehow leaking libc, right? How do we actually do that? Because if you remember, all our chunks are in the heap. Does the heap have any libc pointers? Maybe not. However, there is a very special kind of bin that will put libc pointers in our chunks, right? And this is called the unsorted bin. If you remember from the lecture in the morning, right, we talked about the different bins that the heap uses to store free chunks, right? You'll see that one of these chunks are called the unsorted bin, right? And you'll notice over here that it says that this bin specifically contains libc pointers. So when the libc pointers are put into the chunk, then it's easy for us to read those pointers because they're on the heap as well, right? Okay, so to kind of illustrate this, first we need to know how do we put a chunk into the unsorted bin instead of the Tcache bin, right? You'll remember that the Tcache only accepts chunks up to a certain size. In this case, hex 410, right? Anything larger than that, it's gonna reject. So what we're gonna do is we're gonna allocate a certain a large size, right? Let's say 1072. Okay, this index. I am gonna allocate a 1072 bytes large chunk, right? And presumably because 1072 bytes is larger than the limit that the Tcache accepts up to 410, right? Over here is 430. Presumably, when we free this chunk, it's gonna go into the unsorted bin over here. And the unsorted bin is gonna write some libc pointers to this specific chunk that we allocate. So let's go ahead and try that. I'm gonna now, if I free this chunk that we allocated, hopefully we should see some libc pointers, right? So I'm gonna go into my visual heap, and you'll notice that instead of seeing libc pointers, you just see this top chunk over here and this initializer chunk that's always there at the start of the heap, so it's not really important to us. But the most important question is where exactly is the chunk that we just allocated, right? Um, so let's run that through again, just to kind of understand why this is happening. I'm gonna allocate the chunk first, and then let's view it in the heap. So we did allocate the chunk correctly because it's right there. This is the 430 or plus hex is 440 size chunk. And this is the top chunk that's right next to our large chunk over here, right? Take note of the size. This is gonna be important later on. So the size of the top chunk is this 20,930, right? If now I continue and I free this chunk, we're gonna see the same thing, right? Our chunk is gone, but notice that now the size of the top chunk is larger, right? And if I take the old size and I subtract it from our new size over here, you'll see that it is exactly 440, which was the exact size of our large chunk just now. Okay, so what exactly happened, right? This is something that we call consolidation. And what consolidation is basically this thing where if your large chunk is larger than the Tcache limit, right? It's a it's in the unsorted bin range, but when you free it, it's next to the top chunk, right? The heap is gonna decide that it's easier to merge that chunk with the top chunk instead of putting it into a bin, right? So to kind of understand this from an analogy, maybe it's helpful. We go back to the restaurant analogy, right? Uh, Remember that I said if you have two tables that are empty and are next to each other, it's very easy to just combine them into two like continuous rows of tables, right? So you have a larger table that can service larger groups of people, right? So this is exactly the same kind of logic that the heap is operating on, right? For the heap to be efficient, it has to be able to simplify the arrangement of chunks in the heap. And what I kind of mean is that if there were so many chunks put into the bins themselves, right, it's gonna take the heap allocator a really long time to search for chunks to give back to the user when they request for memory, right? So because of this, the heap kind of decides that it would be easier if instead of having so many bins in the chunks, I mean so many chunks in the bins, it would be easier if instead we, whenever possible, we can merge it back into the top chunk so that it simplifies things down a little bit, right? So kind of like the restaurant, it's a bit simpler for them to think, oh, I can just combine tables instead of allocating it like individually to groups of people, right? So that's the logic, right? Uh, to kind of give another visualization, uh, let's say this is the chunk that we allocated, right? The hex 440 chunk, and this is the top chunk now. So when we free it, it's gonna just combine with the top chunk, basically, because of that consolidation logic that we just talked about, right? So how can we prevent this, right? We know that if the chunk was any smaller, if it was in the Tcache size range, it wouldn't merge back into the top chunk. It would be put into the Tcache bin, but it won't give us any libc leak, right? Because the Tcache doesn't naturally have libc pointers. And if we make it any larger than the Tcache size range, um, instead of going into the unsorted bin as it should usually, it just consolidates into the top chunk. So what do we do, right? Let's go back to the restaurant analogy, right? What kind of condition would cause the restaurant to merge two tables together if they're next to each other, right? It's easy for two like tables that are adjacent to be merged together because uh there's no obstacle in the middle, right? But if instead you had two free tables or empty tables, and in between those empty tables you have like one table that's currently occupied by some people, then it's not so easy to combine them together, right? And that's exactly the kind of logic that we're gonna apply here to prevent our large chunk from merging with the top chunk, right? When we allocate our large chunk, we're gonna allocate also what we call a guard chunk, which is basically this chunk that's gonna be in between our free chunk and also the top chunk, right? And basically, this will prevent our large chunk from combining with the top chunk, and instead it will go into the unsorted bin, right? And if we try this, let's say in GDB, I'm gonna malloc our like very large chunk, and then I'm gonna allocate a little chunk, right? I view this in the heap. You see our large chunk is over here, the hex 440 size chunk. And then after it, in between the actual top chunk and this chunk that we allocated, there's this small chunk, right? And now if we free this large chunk, you'll see that it was put into the unsorted bin, yes, and there are libc pointers, right? Jeff has so nicely indicated this is a libc pointer. It lives in the libc, and it's of course a constant offset from the libc base. I think if we okay, there's no uh okay. So to get the libc base, because we want to calculate the offset of this leak from the base, right? So we can calculate the base. Uh, Basically, I'm gonna take the address that we leak from the chunk, and then I'm gonna subtract it from the libc base. Okay, where is it? It's this one, right? This is the base because it's the topmost chunk that reads libc over here, and also it's the leftmost chunk, meaning this is the lowest address for this memory region, right? So this is the libc base. I'm gonna copy it over here, and we're gonna calculate our offset. So the print command will just calculate this for us. You can see that our offset is 1EC BE0. So when we leak the libc pointer and we convert it into a number, we're gonna have to subtract this specific offset to get the libc base, right? So let's just implement that in our script, right? I'm gonna quit over here. We go back to our solve script. Okay, so we carry out the plan like before. Let's do the exact same thing that we did. We're gonna allocate our large chunk over here, and then I'm gonna allocate a small chunk over here, and this will be our guard chunk. So now when I free this uh, large chunk and I read from the the large chunk that we just freed, this should be our libc pointer. So just to see if this works, let's run our script, this time without GDB. Let's just run it, and you'll see that indeed our leak is a libc pointer, and it's the one that we found from the heap just now, right? So now all we have to do is to subtract the uh, offset to get the libc base, right? Okay, so now I'm gonna print this to make sure our libc base looks kind of correct. And the way that you kind of determine whether your libc base is correct is kind of like uh, if you run a binary over here, right? The libc base is always gonna have three zeros over here, right? 0, 0, 0. And that's usually how you kind of know that the the base that you calculated was correct. And if we run our program, we'll see that indeed our base is correct. This looks correct because we have three zeros over here, and so on and so on. Okay, so we've linked our libc. Let's go back to the plan. We linked our libc. So ideally, that means we can calculate the address of system, right? And when we use our Tcache poisoning to override the GOT entry with system, we can override the entry with the correct libc address of a system, right? Okay, so that was a lot, but now because we have our libc base, right? If we want to get our system address, then we can do our system is equal to libc base plus whatever offset system is from the base. But there's actually an easier way to do this in Bone Tools, right? If instead you don't use like your custom variable for the libc base, and you use the what we call the address property for the libc object, right? Okay, because you'll see over here, Bone init nicely loaded our libc as a separate elf binary, right? All of the elf objects in Bone Tools have this property called the address property. And this is basically Bone Tools' way of tracking what the calculated base address of each elf binary loaded is. And the nice thing about this is that when you want to get the actual address of a, let's say, system, instead of having to calculate like the libc base plus whatever offset it is from, right? I can get this exact symbol by doing libc dot sim for symbols, right? And whatever the name of the symbol that we want from here, right? Like so. And indeed, if I try to print this in our script, oh yeah, this is like a logging utility for libc. What this kind of means is that whatever you pass into the arguments, libc will try to print it as a hexadecimal number. Yeah, that's all. Okay, so if we try to run the script and see whether our system address is correctly loaded into libc, I mean into Bone Tools, right? You'll see that indeed uh, the libc address for system is correctly calculated. Right, this is the base and this is the system address. So that's very nice for us because instead of calculating the offset, we don't have to anymore. Right, we can just simply use Bone Tools to retrieve the calculated address of the symbol. Okay, so now what we're gonna do is we want to put two chunks of the same size into the Tcache, and then uh, we want to override the chunk at the head uh, to point to the GOT entry for free, right? So let's do this in Bone Tools. So we don't need these two chunks anymore, right? So what we can do is we can just reuse those indexes, right, in the chunks array. So what I'm gonna do is we're gonna allocate our two chunks that we intend to put into the Tcache over here, like so. And then remember we have to put it into the Tcache, so we gotta free both chunks, right? So now because the head of the bin is gonna be whatever you last freed, right? So this index zero chunk is gonna be the last freed chunk. Okay, so now we want the the address of the entry for a free function, right? So one way you can do it, of course, is the manual way. We go into GDB, right? We run it, and then there's this nice Jeff command over here, GOT, that prints out the addresses of all the entries. And we can just grab it over here. I'm gonna copy it, and we just gotta paste it into our solve script, right? And we want to edit this zero index chunk to be this address over here. So what I'm gonna do is we're just gonna use our edit helper function, and then for the content, we're just gonna pass in the the address that we want, so free GOT, and we pass it into the P64 function, so we can convert it into the byte string, right? That's the little endian format for this number, right? And when we allocate from the Dcache, right, we gotta allocate twice, right? Because remember, the first chunk is gonna be this zero index chunk, but then the second chunk is gonna be whatever we overrode the address to, right? So we gotta allocate twice, and you'll see that this is gonna be our free GOT chunk, right? And to kind of show you that this is indeed the GOT chunk, what I'm gonna do is I'm gonna attach GDB, I'm gonna run the script. Okay, so we've done our Dcache poisoning. Right, let's see what is in our chunks array. Okay, I'm just gonna do this instead. If you look at our chunks array, basically the way to read this is from left to right and then left to right. The first index is gonna be here. This is index 0. This is index 1. And you can see that indeed this is our free GOT entry, right? So if we edit the index number 1 over here, we're gonna be writing into the GOT for this free function. Right. And remember, our goal is to overwrite this to the system address. So easily enough, let's just overwrite number 1 with the address of system, right? You can pause if you need to copy this code. So I'm just gonna pause over here for a bit. Okay, and then when we run this, just to see if our write worked. Okay, so our code has already performed the write into the GOT entry. If we run this GOT command, you'll see that indeed the GOT entry for the free function is now system, right? And from here on, it's kind of easy. All we need to do is to make a chunk that has our bin.sh string, right? And when we free that chunk, we'll just be calling system on it. So we're gonna go over here, and when I make a chunk with okay, this is wrong. Let's say 24, yeah. And when I edit this chunk with the bin.sh string, and we call free on this chunk, remember we overrode the GOT entry, so now the program is gonna call system on this. And if we run it, you'll see that indeed, this is a good sign. It means that the system function has run, right? And if we go back to our phone tool script, we're now in the interactive mode. And what this means is that whatever we send into the terminal over here is gonna be received by the binary as input, right? So if we do ls, we can see that indeed it runs our command. I do echo pwn whatever. See that it does echo pwn. So indeed we have a shell. And over here you can like cat whatever flag the text that you wanted to read, and we're done. Okay, so that was a lot to take in, but I hope you get the general idea. The idea being that when you're doing a heap exploitation, usually some sub goals is that you want to trigger code execution. And if your goal is just a shell, then of course we need to leak libc, calculate the system address, and we're done. But you'll notice that there's kind of a reoccurring theme usually when you do heap exploitation challenges. Uh, Specifically, okay, let's say I go to the other challenge, right? This is the second challenge that we'll be doing later. But if I go over here, you'll see that the only thing that changed was this target that we were doing Tcache poisoning for. Right over here, um, the plan is to do Tcache poisoning, and then you want to allocate over here. Over here, on the first challenge, the target is this GOT entry, right? So the pattern is usually for heap exploitation. The goal is to be able to gain some form of what we call a primitive, right? Or basically to be able to write whatever we want to wherever we want, right? And in this case, we accomplished it with Tcache poisoning, right? So this is a good mental model to have when we do heap exploitation. Your goal is to somehow be able to gain the basic ability to write whatever you want, to read whatever you want, to wherever you want, right? And uh, in some form or another, that is going to lead you to be able to get code execution in whatever way there is, right? And to kind of demonstrate why this principle is so important, right? First, I'm gonna move on to the next challenge, right? Uh, the next challenge is kind of similar, right? Uh, the only difference, if I go to the second challenge over here, I'm gonna unzip this. If I go to the second challenge and I read the source code, it's exactly the same. There is a sort of ability to allocate whatever size you want in the heap. You're able to free that chunk, and then there's the same vulnerability, this use after free, right? You'll notice that the only thing that's different is that there is full railroad, right? Meaning the target that we were using before, the GOT entry is not viable anymore, but the same method to write to whatever you want is still gonna be the same, right? So this is what we call a primitive. For those of you who are more interested in like learning more of this later on, this is what we call a heap primitive. And yeah, it's the idea that uh, if you have the same, if you what no matter what heap problem that you're doing, uh, you're gonna end up in some way trying to get a a write or a read to an arbitrary location. And this is what we call an arbitrary write or an arbitrary read, right? Okay, but let's go back to this second challenge over here. So some time for you to switch your screen to the second challenge. This is called toddler heap. And the only thing different is gonna be the protections, right? Over here, we have full railroad and we have PIE enabled. So what does this mean? We don't know the base address of the ELF binary itself, right? And even then, if we somehow do know it, we can't write to the GOT table as we did before. So what other things can we attack to get the code execution? And the answer is we can attack the libc, right? So the thing about the libc is that there is this thing called the malloc and free hooks, and these are basically function pointers in the libc where if the free function is called on some pointer and the free hook uh, function pointer is not null, then whatever is inside this free hook pointer is gonna be called onto the same argument. And the same is for malloc, but most importantly, because this free hook and malloc hook are just pointers to some function address, if we can overwrite whatever functions inside this free hook pointer, right, then free and malloc will be calling whatever function we give it, right? And you can kind of see there is a similar idea to the first challenge where we're trying to overwrite a kind of address or a pointer so that whenever this pointer is used to call something, it calls our function instead. So similar idea as the GOT is basically you want to override this hook function pointer with whatever function we want, in this case system, right? And the same trigger of our shell is the same, right? When free is called, actually it will call system on the pointer and so on and so forth, right? You'll see that our plan is indeed similar as well. When you, but instead the target is different, right? This is free hook, and previously it was a global offset table. So different target, but since everything is the same over here, everything else basically, you'll notice that if we copy whatever code that we had over here, like so, I'm just gonna copy everything that we had, and over here, okay, let's run Ponynet first. The idea is that because only the target is different, right, but the solve path is the same, we just need to change the target, right? Okay, let's just wait for this. Yeah, so the idea that because the only thing that's different is the target, uh, the idea is that the sort of primitive or the primitive building block of your exploit is the same. So yeah, this is a very important kind of concept for exploitation, and it will be more and more important as you move up to do harder kind of problems that you may encounter in other competitions as well. That even though the kind of binary is gonna be different, there's gonna be a different kind of application, whatever, and so on. As long as you're able to gain the same kind of primitive or the ability to read or write whatever you want, uh, the solve is gonna be kind of the same pretty much after that. Okay, so it's finished running. There's kind of an error here, but we don't have to worry about it because it linked our libc, right? Okay, so I'm gonna go over here and just to demonstrate why this primitive idea is so important, if instead I change free GOT to something like free hook, okay, and the same thing as before, instead of calculating the free hook address manually, we can just do the same thing that we did with system, right? Okay, so if we just change the target and we run this script, you'll see that we do solve it instantly, right? Over here, it's managed to call system. And if I go to the upper terminal here, indeed, it's running our commands, right? Okay, but why is this so? Because the idea of attack is still the same. We have the same vulnerability over here, right? The fact that we have reduce after free, and the fact that we can still perform Tcache poisoning with that same vulnerability, and so on and so forth. But the only thing that was different was the target. Yeah. But just for those who kind of want a refresher on what we did in the previous challenge, so you can understand the script, right? Again, it was this plan, right? Over here, we want to allocate the unsorted bin chunk, So we allocate a guard chunk, then we free the large chunk. And this gives us our libc leak. And then afterwards, because we free two Tcache size chunks into the Tcache, we can edit the head of the Tcache to point to this free hook, right? Or whatever target it was. And when we allocate twice from the Tcache, it's gonna give us our free hook address instead. And when we edit it, it's gonna replace it with the system address, right? And again, the trigger is the same because when you free the chunk and the chunk contains this binsh string, the free function is gonna call this free hook over here. And because the free hook is set to our system address, it's gonna call system instead. And this gives us the shell. And we solve the challenge and we're done. Okay. So congratulations first. Because uh indeed this is like one of the hardest areas in cybersecurity usually. You might have experienced it yourself. It was a bit hard to understand the concepts if you had very little prerequisite. But the fact that you've made it as far as you have right now is already quite commendable. So don't be discouraged. Hopefully you found this fun. But just in case you want to be able to explore right after these 2 days of content, now one very uh useful resource is this GitHub repository called How to Heap. And basically, what this repository is a collection of all the different heap exploitation techniques. So you'll see that we taught you guys how to do uh, Tcache processing, right? And it's already included in the list. But you'll see that there are some other exploits over here that we didn't really talk about because it might have been too complicated for this 2 days. But if you ever feel uh, like you want to explore outside of just the vulnerability that we taught, the use after free, and you want to explore how to exploit the other bins as well, this is one useful resource. Now, another resource that's highly recommended usually is something like Bone College. And what this is basically like kind of website where uh, they have a dedicated courses for you to explore different parts of binary exploitation on your own. So how this works is that let's say we have one module over here, and they have first they give you some slides, right? Usually it comes with a video, right? But there are some slides on how the theory works, and then there are some challenges, quite like the workshop challenges that we gave you guys, that teach you how to uh, apply the concepts that you learned, right? So this is another useful resource. So with that, yeah, certainly, it's a commendable thing to be able to make it all this way. And if you want to explore further, there is still um, quite a few things that you can learn, right? There are some more advanced concepts. So, for example, the other heap techniques that I showed in the how to heap, but there are also different heap implementations, right? Uh, the one that we just showed you was the implementation for the what we call the glibc library, right? But there are other implementations such as the JE-malloc, which is usually used for Android and such. But the way that the heap works in those implementations are a bit different, and the exploitation techniques are going to be different as well. There are some other concepts that are used to gain code execution, right? For example, we showed you how to gain code execution through the global offset table and also the free hook. But there are other techniques as well. For example, file stream oriented programming is one of those. And this is kind of outside the scope of this lecture, but if you want to look it up yourself, you can. It's a bit more complicated than what we've taught. But if you're up to it, if you're up for it, go ahead, right? And other than like Pwn that we did in the Linux environment, there's also the Pwn in the Windows and Mac OS environments. And these environments are going to be a bit more different. So whatever we've taught these few days, uh, the specifics or the internals might not be the same, but the concepts such as a buffer overflow or use after free, those are probably going to be the same, whatever environment you're in, right? Now, a few other types of pwn could be something like kernel pwn, which is basically instead of exploiting a small executable like this one, you actually exploit the whole system that the computer is built on. This is what we call the kernel, right? And this can let you do some crazy things. For example, if you remember on the opening ceremony day, Lucas showed how to gain a privilege, how to do a privilege escalation exploit, which is basically being able to elevate your exploit. I mean, you elevate your permissions from a normal user to a privileged user, right? And there are also other types of pwn, such as those in the browser, because the browser itself is another piece of software that runs in your computer, right? But the internals itself might be very complicated as well, so the exploitation is going to be a bit different. So these are some things that you can explore on your own as well. And of course, there are some resources that are incredibly instrumental if you want to learn Pwn on your own, right? Many of us over here, we didn't we didn't actually rely a lot on a dedicated kind of training program or such. Actually, most of us started or got to where we are because we're able to learn on our own, to read resources online on our own, and also try to reason through our exploits, right? So to improve this is one of the most useful techniques there. So these resources are kind of useful, and we will be sending these slides to you guys. So once again, thank you for doing this. It's been wonderful, especially for the trainers as well. Right, so we hope you guys have had fun, maybe learned a thing or two, and yeah, goodbye.